Hey, so in this video we'll be going over VESPR theory, which is valence shell electron pair repulsion theory. Alright, so before we get into VESPR theory, let's talk about what will be going on. So when we have two or more atoms that are going to bond together to create a molecule, what happens here is that their valence electrons are either shared or transferred. Now, if it's an ionic compound, the valence electrons will be transferred. If it's a covalent compound, the valence electrons will be shared. Now, what's going on here is that these valence electrons are being transferred and shared in such a way that if there is any lone pairs, and we'll get into that later, but the structure and orientation and the way that they're being shared will determine the molecular structure or geometry, if you will, of the molecule. So before we get into VESPR theory and what that is, let's talk about the Lewis structure. So the Lewis structure was discovered or brought up or derived from a American physicist named Gilbert N. Lewis, and who also discovered the covalent bonds, and he has a huge knowledge of electron pairs. So this is basically the basis of how we start, of how we use VESPR theory. Once we have a Lewis structure in place, then we can develop our VESPR theory, and then after that, then we can develop what the overall shape of our molecule will be. So I'll go over here what the Lewis dot structure is and what's going on. So basically, for Lewis dot structure, it is a geometrical representation of the bonding of two or more atoms. Is what's going on here. So we've already gone over before. Like I said, the important concept you need to know is that we have an ionic bonds, which is transfer of electrons, and covalent bonds, which is sharing of electrons. So the important thing here is that the atoms bond together in such a way that the compound becomes neutral, which is the reason for the sharing and transferring of the valence electrons. So what's happening here is that we have these charged ions, and they bond together. Once they bond together, we'll have a neutral compound. And that's the whole reasoning for the transfer of electrons or the sharing of electrons, because after this bonding happens, after this chemical reaction happens, we want a neutral compound which is going to be stable. So right here we have the steps in creating a Lewis dot structure. So right here I have magnesium 2-chloride, which is an ionic compound, which is what we are transferring valence electrons from one ion to another. And so what you would want to do, the steps here, is you write a skeletal structure for the molecule. So if we know that if we know that there's going to be two chlorine atoms and one magnesium atom, magnesium is going to be our central atom, and the chlorines are going to be our terminal atoms. Now, one specific thing to get a grasp of here is that magnesium typically has a 2+ charge, right? And this is the ion of magnesium. This isn't a neutral atom. This is a ionic. This is a magnesium ion. So it has a 2+ charge, and we know that chlorine typically has a -1 charge. And so we know to make this molecule here neutral, there needs to be 2 chlorine atoms for every 1 magnesium atom. And once the chemical reaction is done, that will create a neutral compound here, or molecule. So basically what's going on here is, first you want to write the skeletal structure of the molecule to be bonded, and first we'll have the valence electron for the central atom in the middle, and then we'll go ahead by filling in the terminal atoms on either side. Second, we'll calculate, let me take that back. First, you want to calculate the number of valence electrons for your entire molecule. So that is for both of your chlorines and your magnesium. Then you want to start connecting the dots for your valence electrons. And the way you want to do that is distribute electrons among the atoms, beginning with bonding electrons first, then proceed to lone pairs on the terminal atoms, and finally the lone pairs on the central atom. So the last thing you want to do is, if your central atom, which in this case is magnesium, has any lone pairs, that will be the last thing that you'll fill in there. And then if we haven't reached an octet in our outer shell, then you'll do double or triple bonds if necessary. All right, so here let's talk about the VESPR theory in action. So what's going on here is, in the VESPR theory, we use a method called the AXE method, with A being our central atom, X being the bonding element, and E being the lone pairs, if there are any. So in this case, with magnesium chloride, we'll have X with a subscript of 2, because X is our bonding element, and since we have chlorine and we have 2 of those, we have a subscript of 2. And then our E will be our lone pairs, and since, as you can tell here, we have no lone pairs for magnesium, so we'll leave that's left blank. Now, what's going on here in the geometry of the molecule is that, hypothetically speaking, if magnesium has a lone pair, both of our terminal atoms here, both of our chlorines, would be repelled, because there's a lone pair of electrons here, and both our chlorines have electrons on either side, so it would be repelled. So it wouldn't be it wouldn't be a line here. Basically, there would be I guess, for lack of better words, a cantation of atoms here. So we'll have, a line going this way and a line going this way, because there's a lone pair right here, and these atoms here are being repelled away from your lone pair electrons on top. Now, since magnesium here doesn't have any lone pairs, we can see that there's no repel on either electron here. So our geometrical figure here is going to be linear. All right. This here is, which we've basically gone over in the last slide, but it's just a chart for our AXE notation. These are the different charts we'll have. So let's say in this case right here, this is our central atom. These are 2 terminal atoms. The 2 terminal atoms are bonding to our central atom, and this right here is a lone pair of electrons. And the reason why there's a cantation here of 120 degrees on either side is because we have a lone pair here, which is repelling the terminal atoms on either side. So in this case, again, like I said, we're just in this slide here, we're just categorizing the geometry of our molecule. So obviously we know that since we don't have any lone pair here, we have a shape. The shape here is linear. So in summary, VESPR theory can be supported by using these techniques and visualizing the molecular geometry of a molecule. First, by calculating the number of total valence electrons, and then creating a Lewis dot structure for those electrons in the bonding atoms to create our molecule. And then from there, we can decide the geometry of the molecule based on the number of atoms being bonded and the number of lone pairs we have in our molecule. One last thing here, I will go into our PhET program. this here just gives us sort of a 3D look of what's going on here. So if you now obviously these aren't named, but this is just, if you look at it, this is our 3D model of magnesium chloride, if you will. And you see what's happening here. We have an angle of 180 degrees from one bonding pair of electron to the other, which are both connected to our central atom. So in other cases, if we had a different one, that angle would be different. But since we only have two chlorides bonded to our central magnesium, this is the total angle in between here. And so, yeah, that is VESPR theory. That is Lewis dot structure, and that is how the Lewis dot structure help us create VESPR theory and the geometry of a molecule.